Mom. Can you hear me?
Yes.
Cool. So let's start with the theater. Hey, Matt.
Yeah, Heiko.
You know what? We open sourced the source code for our Compass app. You know, that shiny thing that follows your arm? We introduced that with firmware 2.5, I think. And it's super cool to have that open source, but now that it is, I feel a bit embarrassed since there are so many to-dos still on that source code stating, get rid of me, get rid of the floats. I don't know how, since, I mean, getting rid of floats and converting that to ints is, it's not an easy task.
Well, Heiko, I've got a fix for you. When I ported OpenGL to the Pebble, it's called PebbleGL, I had a drop-in floating point to fixed point adapter, so you don't have to modify your code, but everything under the hood is being done in fixed point for you. You save some code space, and you get a little bit more performance.
Well, that sounds great, but wait a second. OpenGL on a Pebble?
Sure, why not? Like, with the Pebble, sky's the limit. You know, do whatever you think you can, and it's a pretty impressive system. I'm using lighting sources.
Stop. Lighting sources, that means gray. Do we have a color display now? Or, I mean, it's black and white, isn't it?
Right. So what I'm using is dithering, where we're actually using checkerboard patterns to create the appearance of gray instead of actually having gray on the display. But because we have such a high DPI, it looks great.
And I bet you had problems to fit that into 24K, and I can tell you a lot about that. Actually, I can tell you a lot about that. And this is what we are going to do the next 3 hours. So all of the stuff you heard during that conversation and a lot more you will hear during that 3 hours. We split that into 3 parts, actually. We start with size. So how do you squeeze more into your Pebble app? And then we have a short break. After that, we continue with graphics, including runtime, dithering, and fancy other stuff. And we conclude with a third part. I'm not sure how Tomar called it. I call it 101 double or quadruple O. That's the final part before we go to the meetup. Okay, so I'd say we start with size. Who of you ever had problems with your PBW size? Okay, that's roughly half of the audience. There are different problems with size. It is the code size as well as the resource size. And typically what you have when you compile is something like that. You type in the Pebble command, Pebble build, and somewhere in that cryptic log output you see app memory usage. And that is the code space you have. Whenever you try to do something like printf, you will see it won't compile anymore. It's too large. Or when you put in all the little snippets you find on Stack Overflow, your code is too large. And once you use some floating points, another few Ks are being added to your code space. And in the end, that is quite interesting to look at. So it says you have footprint and then also available heap. The reason is those two fight with each other. When your code size increases, your available heap will go down. And this is since you only have a limited amount of RAM, and we want to give you the most out of it. So we give you all the available RAM that is there after we loaded your binary. Whenever you increase your code size, you will have less heap. But a quick question: does everybody know what code segment and heap means? So who does know what heap is and what code segment is? That's a couple of you. Great. We play a little game after the lunch, so you will wake up. We have 2 segments here. That's A, the code segment, which includes static variables as well as the actual binary code. And we have segment B, that is heap. Technically, it's not a segment. OK, so let's start. That one here, where does it go? A or B? Dum, 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 dum. What? B, A, what? Ooh, stop. Who's brave and called something? A. That's right. That's a static variable that goes to the next to the code you have. OK, another one. That one here. Where does it go? B. That's B, right. So even though we are writing now to the variable that you just discovered is on A, we are creating a new object on the heap. We are not calling malloc, but instead we call a function that comes with the SDK and will create something on the heap on our behalf. That goes to the heap. That's great. OK. Where does that go? String literals go to your code space. And that's especially annoying when you deal with applog. So the longer the statements are that you use, the more code space goes away. Be aware of that. Maybe you introduce if-defs for your final application or if-defs for various parts of your log statements. Every single string literal will go into your code space. And you can outsource them. For example, you can load them on demand from persistent storage, like some apps do. And we will talk about that later. OK, that's A. Now, where does that go? B. No. Francois, on the stack. OK, that's a trick question. That's actually C. So we have more than our 24K. We have more RAM. We have not only our code space and heap space, we also have stack. And that's pretty interesting. So that one here is the last one, just to get into the rhythm. What is it? It's a pointer to the heap. So where does it go? Again, it goes to the stack. So that function here returns something that's already on the heap when you created the window, and the result will be stored then on the stack. OK, so now that we know what heap is and code is, and also what stack is, quick reminder what you can do with a stack. Whenever you call a function, or you have local variables, or even create arrays of dynamic size, so yes, you can perfectly do that, create an array of a struct, and its size is an argument you got in a function, you can put that on the stack. And super convenient. The runtime will clean after you. All that goes on the stack. So we have the 24K you saw earlier, plus additional 2K on the stack. Be careful, though. This is at most 2K. Most of the time, you will not have that space at all. So at this point, when I was first writing for the Pebble, I was a bit surprised why it's only 24K. On Wikipedia and other sources, you can read that there is more RAM memory available. Why is it only 24K? Yes. So this is the hardware we are running on. I'm not sure if you ever saw that picture. It's not a test circuit board or anything. This is really the hardware that is in steel or in the original Pebble. And the largest part of it is the battery. And then you see that chip on the bottom left, which is not the CPU at all. That is actually our persistent storage. And a couple of other components, such as the magnetometer you just got access to, as well as the accelerometer. That one here is the microcontroller, the CPU. And if you read carefully, it has 128K of RAM. So why is it only 24K for us? Since on that 128K, everything has to be managed on. And that includes the kernel. So we have a Bluetooth stack there, which eats up a lot of our available memory. We have a multi-threading operating system that runs several threads in parallel and manages all the stacks. Now we introduce the background workers, which take some memory as well. And then we have additional space for your application, 32K to be precise, which is still not the 24 you read about earlier. Yes, since we have to manage your app. So you got an exclusive frame buffer, something we will talk about later. And also, we manage your scheduler for animations and, well, basically some bookkeeping. And that takes 6K, which will bring you 24K plus 2K of stack. OK, so we're not cheating here. We're not betraying you. This is all you can get. And you have to deal with it. So whenever we talk about RAM or app, we are only talking about what's accessible to you. And this is only that lower part here. Perfect. But it's not that your space at hand is limited to that 24K. Think about it. We introduced a lot of APIs to extend that. So first, we have persistent storage. You can store up to 4K into flash memory. And you can read out of it again. Think of it as a hard drive for your application. Yes, it's slower. It's not too slow, though, but you can still read and write to it. And we have the resources. That is read-only, granted, but you can put a lot of additional data onto that. In addition to that, we have the ability to talk with app message to the phone, right? And from there, you can literally store an infinite amount of data. You can download the whole internet onto your Pebble if you want to. And you can store it back. So technically, that one is an external storage at your hand, or wrist to be precise. OK, now that was for traditional apps. Now that we introduced background workers, those numbers shift a bit. So we have less stack and less heap available to the background worker. And also, not all the APIs are available for background workers. That includes app messages, and also you cannot access resources at all. You can use the persistent storage, though, and you can even use that to communicate between the two parts of your application. So this is just an overview to give you the numbers. I already mentioned that briefly. So I think stack and code size is clear. And then we have different APIs you're all familiar with to access the different parts of memory that are available to you. Okay, this is just a recap why it is constrained. We are running on an embedded device, and it's only 24K for you, and it's only limited flash. And we, as a developer, want to make the most out of it. Okay. What you see on the left now will be our outline for the presentation. It's not that we are going from top to the bottom. It's not that everything will have the same amount of time. In fact, the JavaScript and native code part is not covered at all during that presentation. But think of that as an outline, so we will cover all the pieces you saw earlier. And the first one now is code size. Do you have a feeling how large your code actually is? Let's prove that. So if I write that function here, which takes a byte, a uint8, and just multiplies it by 3 and passes it over to another function which accepts an integer, how large is that function anyway? How many bytes does it take? Any guesses? Pardon? 64. That's a lot. Any other guesses?
20.
Pardon?
20.
20? It's even less. So our ARM Cortex-M3 processor, especially the Thumb2 instruction set, is well known for its high density. It's only taking 8 bytes. And you can learn that actually by looking at the assembly. I'm just rushing over. So who's able to read ARM assembler here? Okay, that's the firmware team, and then a couple of you in the audience. So what it does is, actually it loads the value, the literal 3, into one of its registers, and then the calling convention in C, actually in the ARM ABI, is that in register 0 is the argument, which is now the I. It will be multiplied with the value we had before. Now we have in R0, we have our new value, and we now branch to use value, the actual function call, without storing in the link register the address it has to jump back to, since whenever use value is ready and has done whatever it did, it will just jump back to where I should jump back to. And that way, we only need 8 bytes of memory. And in total, that app here, I mean, I was using the standard template, writing that function here, it's only 266 bytes. If you are curious how you can get to that information, with your SDK on your hard drive, there's the ARM toolchain. And I think it's Pebble and then ARM tools or something, and then bin. And in the end, you will have this object dump command. For me personally, it's on my path, so I can always type it. But you will find it somewhere there. And you can even, if you use the L argument here, you can even see for each assembly line the corresponding C code where it originally came from. OK, so that's 8 byte. Now, our requirements change, and instead of multiplying that number by 3, I'm now multiplying by 1.5. That means I'm changing the second argument from being an integer to being a double. Here's the code. Any guesses? How large is the function now?
64.
32. Oh, wow, that's a good guess. Actually, it's 32 bytes. So you might think, well, it's a few K that's been added each time I'm running that float, but that function in particular is only 32 bytes. I'm not going over all the details here, but what you see is it actually calls different functions. It calls a function, these I to D, which converts the integer to a double, and then it does the multiplication with D mul, and then also it converts it back to an int, so use value can be called. So it's actually 3 functions that are now being called, and those functions hadn't been written by you in the first place. This is emulation code. Our hardware doesn't support floating point units at all. So whenever you do that, we have to put additional code into your code size, into your binary, in order to handle that. And here we are calling 3 functions, and if you see that at the bottom line, from 266 bytes, we are now at 2K, just by adding a dot. Okay, so let's have a look. Why is it that large if that is only 32 bytes? Well, if you look at the I to D, that's additional 34 bytes, and that function calls this add F3. And if you look at that code, well, That's a bit longer. And if you can see, it jumps to other functions as well. And so in the end, on the long tail, we will have 2k just by adding that single dot. Okay, that one here in particular is only 360, but I think you get the point. So that's super verse. Whenever you can, try to avoid floats. And there's an easy way to do that. Instead of, in that example here, instead of multiplying by 1.5, you can just multiply by 3 and divide by 2 afterwards. Mathematically, it's completely equivalent. So if we do that and ignore any potential overflows or anything, then we come to that function here, which only uses integers. Now, how large is that?
10 bytes.
10 bytes, exactly. So we are now having 10 bytes, and that means in total, we are at, sorry, that was the quick, 268 bytes again. So we do optimize for 2k just by swapping some numbers. Okay, so from that, yeah.
So basically, all the floating point libraries are statically linked to the binary. So there is no kind of like shared library can be used on the system.
So the question is, isn't there a shared library so all apps could just reuse that floating point stuff? No, it's really that we statically link that emulation code, but we are a bit clever here. We only link what's actually needed. François has an addition.
And the firmware actually doesn't use any of these numbers, so we won't have these functions in the firmware at all.
Yeah, that's a good point. So we avoid floats at all in the firmware. We are recording this, and we have a QA session in the end. I would say, in order to make that smooth, keep your questions till the end, so we can answer them then now. Okay, cool. So starting from there, with the knowledge that we can avoid floats to gain back size, I'm handing over to Matt to give you a case study.
Thanks. So a while ago, I was writing a Mandelbrot application, and I basically just found on a Rosetta code an example of Mandelbrot, and all of the code was in floating point. And of course, as Heiko was saying, like floating point, it's IEEE. The representation isn't supported on our ARM, and the actual way that floating point works is rather complex, as the assembly code was showing, just for multiplications and additions. And for floating point, we're talking about all the floating point operations: multiply, divide, add, subtract, sine, cosine, tangent, conversions between the different formats, if you're going from int to double, or int to float. All of that must be emulated in software. So every time you use any of those functions, you're pulling that code in to support that. Fixed point math, on the other hand, is where you're basically dividing up your amount of bits for your container. So in the case of, if I have an 8-bit container, like a byte, if I use half of it for integer and half of it for decimal, I'm going to reduce my range, but I'm going to be able to represent things as fractional numbers like 2.5 or 3.7, as long as it fits within that range. There are alternatives. There are these fast fixed point libraries that will do all the lifting for you. And one of my favorites is Sine Long Long Math. It's used in a lot of software OpenGL engines, as we see at the link down there, lib3d. What this does is this has special ARM assembly code to handle double multiply, double add, and some carries, all in ARM assembly. And it uses the double container so that we have 32 bits for integer and 32 bits for decimal, so that we keep a large range in both sections. So here I have, on the left, the software floating point version of the Mandelbrot app I just mentioned. And on the right, I have one that's using fixed point wrappers for Sine Long Long Math. So this is the exact same application compiled 2 different ways. So 1 frame, 2 frames, 3 frames, 4 frames, 5 frames, 6 frames, 7, 8, 9, 10, 11. Is the other one stuck? 12, 13, 14. Oh, there we go. So this one is 14 times faster than the other one. This one generated 14 frames in the time that one generated 1. And this is the difference between emulating IEEE float versus having wrappers that allow you to do it in fixed point representations, which the ARM hardware can do for us. Comparing those 2 applications, for code size, we see that the floating point is 10K. The fixed point one is 2.7. We still have to pay for that fixed point support that we're pulling in, but the cost is much lower. And then the interesting thing that we saw in the last demo, the seconds per frame, not to be confused with frames per second, it took 20 seconds to generate one frame with the floating point emulation. It took 2 seconds with fixed point to generate that same exact thing, so 10 times faster. So one of the problems, though, is that a lot of times you don't want to go through and convert all your code. So here we have an example of what conversion would look like, similar to what Heiko had. So on the left, we have floating point. I've got the numbers. I just say float rotation, set it to a value, multiply it by something else, and it just works. In C, we can't overload operators. So if we want to use fixed point libraries or fixed point, like libfixmath on Google Code, we actually have to use these rather ugly functions instead of using multiply, divide, add, or subtract. So you can imagine if you have A times B plus C divided by D, it's going to be a bunch of these wrappers around each other. It gets rather hard to read, and it's also very hard to port. One of the things I was looking at why I did this application was, is there a way to make this easier for myself and for others? We came up with the idea of wrapping how GCC does it. GCC knows that you have a double times a double, and it's going to call these EABI, well, in the case of float, a float multiplication, float times float. I can't overload the operator, but I know if I have these two container types, it's going to call this function with them. So because in the last example, signed long math is 64 bits, I say, well, doubles are 64 bits, and they're a floating point. But if I use that as the container type, and inside of there put my signed longs, I can have the compiler call AEABI demul for me, and in essence, overload the operators. So you can see on the bottom here, I had to do a little bit of work for the constructor where I'm taking this value and basically jamming it into the double container. So the compiler realizes the double, it's still called the type of double, but then I can do direct multiplications that'll trigger AEABI, double multiply. And once again, we have to wrap the constants. So I put this math wrapper on GitHub. This is just a quick example of it. It's generating fractal trees. This demo pulls in more use than just add, subtract, multiply, divide. It's also using sines and cosines, and it's randomly generating the tree. In this case, because we're pulling in the sine and cosine, those are also things that typically we have to emulate. So for code size, we're going in floating point from 9K down to 2K. So we have a 6.3 kilobyte savings. And then for frames per second, since this operation is a little, we're not directly wrapping everything, we're actually calling these functions, we're getting almost twice the performance, but not the tenfold we saw earlier with the direct Mandelbrot. And so these are the links to the two things I presented, the Mandelbrot generator that has both software floating point and the fixed point wrappers. And then the second one, TinyMath, is basically a drop-in into your project where you copy in this one C file, you modify your W script, and you compile, and you basically just get all of your floating point converted under the hood for you to fixed point. All right, with that, back to Heiko.
Thanks, Matt. That's all about code size. So whenever you run that command and see this 9K, you now know what might cause this in the first place, and also use this cryptic assembly to learn more about it. Well, to be honest, we already have a tool that makes that easier. So when you run Pebble analyze size on your project, you will have some information. It's not on the granularity of functions, but on file. But anyway, you can already determine where your size goes, and maybe that and the other hints we gave give you some clue how to optimize your code size. So to sum things up, what you should do is you should avoid anything that bloats your code, and that is, for example, long argument lists. While it is good code practice to have arguments in the first place, it is way cheaper to have singletons, since you have that address only. And if you look at your program closely, most of the time, Pebble apps tend to have singletons. There's a single window most of the time, or for watch faces at least. And then all those have layers as a singleton. You can directly address them. Even though in computer science university lectures, you will be told to avoid that to reduce code size, it's a good practice. Also, applog and string literals in general will bloat your code. And then Sometimes, so the compiler is pretty smart, but it's not that it's always the smartest. You can use attributes on your functions to either avoid inlining or inlining, and you can also avoid macros over functions or functions over macros, and sometimes that is better and sometimes the other is better, and the bottom line is you have to measure first. Whenever you try something and optimize something, measure, change something and measure again. It's absolutely worse to do premature optimization here. Here again are the two commands at your hand, and if you browse a bit in the object dump --help documentation, there's a lot of things that can answer for you, including size for a certain function. Okay, so that was cosize. Now we go to heap. That is actually the 24K you saw earlier, or again, it's complementary. So an advice here is whenever you deal with heap, check the results of malloc and check the results of any of our SDK functions _create. Those will create objects on your behalf, and when you are short on memory, they might return, or they will return null. Now, once you work with those objects, then you will dereference the null pointer, which might crash your application. I strongly encourage you, and I see many bad examples, including my code, where I didn't check that and ultimately crashed the application. Second, we recently introduced, I think in 2.4, heap bytes free and heap bytes used. So you can check for yourself whether you are leaking, how much heap is available when you enter a function, and localize where your heap goes and also how much more is available. And then also be aware that we might take away some of your heap memory. So every time you create objects or register timers, I think it's obvious that you will have an impact on your heap. But also, when you call gpath draw filled, for example, that very same implementation will take away your heap space while it renders that path. And that might cause in strange behavior where nothing has been drawn, even though your gpath is right. I think it's not really documented, but just be aware of it. It can be the case that you are running short on memory and we cannot fulfill your request. Okay. There are some good practices, best practices. So unload resources as soon as possible. So whenever you unload a window, unload your resources, and then also learn more about the actual life cycle of your layers, of your windows and all that, and get rid of anything as soon as possible. Actually, there is a in-depth presentation from Ron and Gregor. Where are you? Just raise your hand. That will be there and there. That will be later tonight at the meetup, and then also tomorrow at 3:30, where you can learn how to do that. And one thing I'm really looking forward to is dynamically loading of code. So we don't, on Pebble, you can execute any code anywhere on memory. That means you can either self-modify your existing code, or you can generate code on the fly, or you can load it from the 4K persistent store or your 96K of persistent store. Essentially, it's like DLLs in Windows, and those two guys will tell us how you can do that. And it's super exciting, I think. And just to stress this, those two don't have access to the firmware. They figure that out all themselves. And it's super impressive, I think. I encourage you to do something similar with the knowledge you have at hand now. Okay, but the bottom line is always check the result of malloc or create functions. So stack. We saw that the stack will implicitly used, but you can abuse it a bit if you want to. So that one here is directly taken from an earlier version of the Compass app. When I did that, I allocated object on the stack directly. So that here, there's the line that's of interest. So I created a struct locally in that function. I created an array dynamically on the stack, and then I was using that array to pre-calculate coordinates and then transition between them and whatnot. That worked fine until num segment grew too large. Since once you exceed a certain amount, your stack will overflow and your application crash. And that is super annoying. Whenever you deal with a stack, and techniques like these, be aware that it can be that you are running out of stack, which ultimately, for me, raises the question, how much stack do I have at hand anyway? And to answer that question, you have to dig a bit deeper. First, your code, all your functions will implicitly, sometimes invisibly, require stack space. When you modify your WScript file, which describes the build, whenever you hit Pebble build, it will look in your WScript file on the root of your project. When you modify that and add a C compiler flag to that file, you will get a pretty nice output. Sometimes it's ticking too fast. You will have that pretty nice output in your build folder, stating exactly how much stack each function will require. And that is static, and then for the example we saw before, you will see a comma dynamic next to the static, since you cannot statically answer the question how much stack a function will have when it's relying on the argument. But anyway, that one is a good first thing, to have a static analysis of your stack. At runtime, you can do some assembly wizardry to obtain the stack pointer. Technically, you could also declare a local variable and get the pointer to that, but I think that one here is a bit more concise. So you will have the initial stack pointer when you add the main method, store that somewhere in a global variable, and whenever you enter any update proc, for example, you can use the same technique to obtain the current stack pointer. Now, the interesting thing to mention here is, even though those two update procs are not being called by you, but by our SDK or APIs, and there is no real visible call stack to you, at these two different points, and I'm calculating the difference, of course. At these 2 points, when I log this, the available stack space is different for both of them. And that is because somehow our implementation, before we call your code, does something. And if you think about it, having a layer hierarchy, maybe it's been implemented in a recursive manner, so that will take up some stack space, and then it's only been called here. So keep in mind that we are messing with your stack as well. So whenever you are being called, it might be that some of your 2K stack space is already been taken by us. So you have now the ability to check statically how much stack space your functions will take. Also, you can measure at runtime how much more stack is available in order to take advantage of that additional RAM. Be careful. Don't use the stack until the last extent. Whenever you call something, it might need additional stack. So whenever you call a function then that draws something or anything else, you will need additional bytes for that, and you don't know in advance how many bytes that will take. So it's just a tool to measure in which region you are. Is it more like 1K available, or is it either 200 bytes? Okay, so that's stack space. I'm really rushing over that. And with resources, I'm handing over back to Matt to give us a case study.
Thanks. So one of the things I love with the Pebble is we have a great display. I was trying to come up with some cool apps to write to use our display in a fun way. And I don't know if any of you guys know the Xkcd comics by Randy Monroe. He makes them all Creative Commons, so you can basically take them and put them in your own applications. You can make trapper keepers and t-shirts out of them. So I thought it'd be fun to make a comic viewer for the Pebble. So when you put images in your resource folder for the Pebble to put in the application, we actually convert the images for you over to PBIs, or Pebble bitmap images. The Pebble bitmap image is like the legacy bitmap format, where it's 1 bit per pixel. And for the way that we render it, we make everything word aligned. So for a full screen bitmap like I have here, it's going to be 160 wide, because it's 144 plus padding to the next word, times 168, our height, divided by 8, so we get bytes, divided by 1024, because we like to read it in kilobytes, and it's 3.3 kilobytes for that one image. For our resource size, we only have 96 kilobytes that we give to applications. So if we're using uncompressed bitmaps, or PBIs, at 3.3K each, because they're always going to be the same size if they're full screen, that allows us only to have 29 images. Well, 29 images doesn't make a great comic viewer. That's like 10 comics. You go through that in a couple of minutes. But uncompressed in memory, that's still going to be 3.3K kilobytes. So when you load it from your resource, uncompressed, into memory, still uncompressed, it's going to be the same size. So I looked at like how would you do this better, and so I looked at using PNG directly, like porting PNG over to the Pebble. That's compressed bitmaps. It's actually just running the Huffman zip compression on the original bitmap with a little extra filtering to give us some extra space. So there I have the exact same image. I'm going from 3.3 kilobytes that we're going to store in resources down to 0.9 kilobytes. So it takes me from 29 images to 106 images, just over 3 times the storage. While we're rendering these, the system still expects it to be a bitmap that it can blit. So even though in the resource we're only paying 0.9K, in actual memory it's going to be uncompressed for 3.3 kilobytes. So it's going to be the same under the hood while we're rendering it. But in terms of resources, you can store more of them. Or another example is you could send it from the phone to the Pebble about 3 times faster. So when I was porting over the PNG support, I used it in a couple of my applications. I made the library available on GitHub, and I found that when we were trying to explain to other developers how to use it, it was in pretty sorry state, where you had to call this, allocate this, have it run the decompressor, and then you finally got the gbit map out of it. So as a convenience, the entire PNG library available at the PNG demo down here is one function, gbitmap create with PNG resource, which is made to mirror gbitmap create with resource. So it'll give you the exact same thing, and you're just giving it the resource handle. So you can add this to your applications by just changing and adding 3 extra characters there, and switch from using bitmaps directly to using PNGs. And then here's the source code for both of those, if anyone's interested. We actually sent 2 pebbles to Randy Monroe with the Xkcd app preloaded on it. And he was really, really impressed. He was really excited about it. And he wrote us back saying, the images on the Pebble look great. The original images are pretty large, they're all hand-drawn. So when you scale them down to fit on the Pebble, you should get some aliasing, but these images look great. Did you hand edit every one of those 106 frames? We did. Every single one. We went through, did them pixel by pixel. Luckily, I had help from Stuart here, who made Tiny Bird. He helped me go through the last 30 or 40 images, because that's a lot of time. So if you guys catch him, thank him, because it's a really great app. Thanks.
Okay, so we are now entering the external space, so anything that's not directly in your application. And that is, for example, the persistent storage and also app messages. So I was struggling to find a really good example that's well known. One of them is Canvas for Pebble, made by Steve. Where's Steve? There's Steve. So what that does is it extends, so whenever you configure in Pebble Canvas an application, basically it's a tool to have building blocks, and you configure a watch face on your phone, it stores that data on the watch. Even though technically it's not really necessary to do that. I mean, each time it could reload what it has to look like and reload all the images. You can use the persistent storage to do so. I can personally think of a couple of other ways to abuse the persistent store, just as a kind of a temporarily storage system. But I really don't see any application out there in the wild. If you have such an application, please tell me. I'm really looking forward to that. The other way to extend your memory at hand is just asking the phone for it. When people ask me about, so does the Pebble always have to have a phone? I'm always saying, well, think of the phone as the back end for your watch. So you can write your application without internet connection, but you can do so much more when you have the back end at hand. And, well, that back end has its own storage, or it can ask the internet. It can do whatever you want. All the heavy load can then happen in JavaScript or in native code, and you just ask it via app message. Okay, so we're pretty good in time. Here are the topics we covered during the last 45 minutes, and here's a recap. So for Stack, there is an alternative to heap memory. you can super easily create an array directly on the stack. You can have variables on the stack that are traditionally on the heap. And in fact, when you think back to SDK 1.0, there was no heap at all. So sometimes it's worth to think what you can put on the stack to get rid of that 24K limit. Be careful, though. Code and static variables and all that, I cannot stress that enough. Before you try to optimize something, so some people say do a loop instead of unrolling your loop and doing 3 times the call. It depends. It really depends. And you have to measure that to see if that's really an optimization you're currently doing. And then, well, Heap, always check the result of malloc. I had so many crashes for apps. And yes, persistent store can be abused. And resources that we just saw can be compressed. And that's super, super impressive, I think. Having, what was it, 200 frames for your animated ping application, 200 frames and a single full screen frames on a single application. You will see that in the next talk, how Matt accomplished that. It's just impressive. Now, think of that. You can store, I already said this, string literals are large and bloat your code size. Well, yes, then put your strings into your resources. But that is limited as well. There are only few cases where you can get a better compression ratio than with strings. Compress your strings. Think of a simple decompression algorithm and compress your data before you put it into the resources. By using a compression algorithm when loading it can save you so much more space on the resources. Take advantage of that. And then here, as I said earlier, understand the phone as the backend. When you think of it of that perspective, so a rich JavaScript application in your browser and the backend, maybe that gives you another perspective what your phone is actually useful for. Okay, so with that, this is the speaking part of our presentation. We have now, I'd say, at least 5 minutes for questions. Thanks.